Dear students, in the last class we discussed on the topic dual nature of matter. This dual nature of matter, this was proposed by de Broglie. The hypothesis says that moving particles are associated with the waves. The waves are called the matter waves or de Broglie waves. These things we discussed in the last class, and there we derived the expressions for lambda. Lambda in terms of energy, momentum and voltage. So lambda, the de Broglie wavelength, is given by h by p. Lambda is also given by h by square root of 2me, where e is the kinetic energy of the moving particle. Lambda is also given by the formula lambda is equal to 12.27 by square root of v. These things we discussed in the last class. So the theory for matter waves was proposed by de Broglie. Now the experiment which confirms the existence of those matter waves. The experiment is Davison and Germer experiment, which confirms the existence of matter waves. The experiment confirms that any moving particle is associated with the wave called the matter wave. And this Davison-Germer experiment, setup is like this. It consists of a filament, a heated filament, and an anode, a metal plate as the anode, and a target, nothing but the nickel crystal is the target here. And this filament is heated electrically, electrically heated filament, and this filament acts like the cathode, maintaining negative potential. This metal plate maintaining positive potential. A high voltage is applied here between the cathode and the anode. So this one acts like the accelerating anode. And these things are maintained or kept in the vacuum chamber. Evacuation is maintained there. This is the experimental setup used by Davison and Germer to prove the matter waves. And the experiment is here. This filament is heated electrically. So electron emission takes place. Thermionic emission takes place here. Electrons are emitted. Those electrons are emitted and they are accelerated towards the anode. So this is the accelerating anode. They are accelerated towards the anode. A potential difference is maintained here using this source. Those accelerated electrons that travel along this path. This is the electron beam. The electron beam hits the target, nickel crystal. Hits the target. And the electrons, they get scattered from the different atomic planes of the crystal. They get scattered from the different atomic planes of the nickel crystal, and they get scattered with certain angles, say theta. This is the angle of deflection. We call it as angle of deflection. They get deflected, and the deflected electrons are collected by a detector. This is a movable detector which collects the deflected electrons at different angles. See here, this movable detector, movable means you can move it along a graduated scale. Graduated scale, the readings vary from 0 to 90. In between that, you can vary the angle of deflection theta. By moving this movable detector along that graduated scale, it is possible to collect electrons deflected at the different angles. The detector collects the electrons deflected with different angles. And this movable detector, see, it is not shown here. This movable detector is connected to the galvanometer, so that whenever the detector collects the electrons, deflected electrons, galvanometer shows deflection, or it measures the current, or it shows the intensity of the electrons deflected with that particular angle. Say for example, suppose the electrons are deflected with this angle, this detector detects them, collects them, and the intensity of those electrons is measured by the galvanometer connected to the movable detector. This is the setup used by Davison and Germer. And here, see, by moving the detector, it is possible to collect electrons scattered with, deflected with different angles. So that, and one more thing, here, electrons, the intensity or the current registered by the galvanometer will be different for different angles theta. And if this current is plotted, this is a radial graph. Here, at the voltage, when the potential difference maintained is less than some 40, less than some 40 volts. In that case, if the graph is plotted, see here this incident beam, the graph plotted here is, see, these lines, they indicate, see, here we divide this angle 90, these are the different angles, see these are the different angles of deflection, different angles of deflection, and these lines represent the current or the intensity registered by the galvanometer. How the graph plotted is, by varying the angle, by varying this angle, by moving the detector, one can change the angle theta. By moving this, you can change theta. By changing theta, corresponding intensity are registered, noted, and see here. Suppose this is the intensity corresponding to one angle, say theta 1, say some 20 degree or 10 degree or 20 degree. So this is the intensity. So this length gives the intensity or the current corresponding to that particular angle. And for another angle, next angle, so intensity. And for the another angle, intensity. This way, like when we plot intensity corresponding to different angles of deflection, and a smooth curve is obtained. A curve like this, a very smooth curve is obtained for a voltage less than 40 degree, around 40, less than some 40 degree volt. I'm sorry, less than 40 volt. And the potential difference is less than 40, a smooth curve like this was obtained from the experiment. And in the experiment, gradually the potential difference between these two electrons and this anode gradually increased, and at an voltage of 48 volts, when the accelerating potential was 48 volt, the curve obtained was like this. At 50 degree, for an angle theta equal to 50 degree, a small increase in intensity was observed. There was an increase in intensity compared to the other angles. Further increase in the voltage. At the voltage 54 volt, the intensity at 50 degree, the intensity was 50 degree was going to be higher, the maximum one. Further increase in voltage. When the voltage was made 60 volt, the intensity is going to be less. And such a increase and decrease in intensity was observed at the given angle 50 degree, corresponding to different voltages. As the potential varied at 50 degree, theta 50 degree, increase the variation of intensity was observed, and the intensity was found to be maximum, corresponding to 54 volt. For all other, there was decrease, slow decrease, and at one point minimum further increase. In this way, a diffraction pattern was observed, corresponding to theta 50 degree, a diffraction, variation of intensity, as you have studied in your previous class about in diffraction. When diffraction takes place in double slit, the diffraction pattern consists of a central maximum. On either side there will be minima and maxima. First minima, second minima, first maximum, second minima, alternately, and so on. Such a pattern was observed when this angle theta, when this potential was varied, corresponding to this 50, angle 50. And the maximum intensity was observed at theta equal to 50 degree. And if you consider this, see here, if you consider the Bragg's law for diffraction here, what happens is the electron incident on the planes of the crystal, the Bragg's planes, the planes are called the Bragg's planes. These are the Bragg's planes. When the electron hits the Bragg's planes, atoms in the Bragg's planes of the crystal, the electrons, they undergo diffraction. Because of this diffraction, such a pattern of variation in intensity, maxima and minima, is observed. The electrons undergo the diffraction. And if you consider the two Bragg's planes, say these two are the Bragg's planes, this is the incident beam. The diffraction is at diffracting angle is 50. And if you draw the normal at this point to the plane, so this is the normal drawn to the plane at this point, normal drawn, so that these two are 25 each, bisects, these two are 25 each, so that this angle between the surface and the incident ray, called the glancing angle is 65 degree. The glancing angle is 65 degree, and The electrons here, they follow Bragg's law. They undergo diffraction following the Bragg's law. The Bragg's law for maximum intensity is 2d sin phi is equal to n lambda. Here phi is glancing angle. 2d sin phi equal to n lambda. And d is nothing but the separation between the two planes. The separation is nothing but d. This is taken as d. And here, see here, why this 2d sin phi is called as a path difference. The path difference between these two rays. After diffraction, these two rays, they move parallel to each other, they interfere to produce the maximum. So that path difference between these two rays is given by 2d sin phi. See here, this we have considered these two rays. The first one deflected. This is the ray, this is the incident one falling on this plane. Incident ray deflects. Next, the ray is falling on this atom. It gets deflected from this atom. So that then deflects. Then it gets deflected. So that the second one travels the path. This plus this. D plus D. 2D. The path traveled by the second beam is 2D more than the first one. So the path difference is 2D, and because of this angle it is 2D sin phi, and this is Bragg's law. So Bragg's law for maximum is 2D sin phi equal to n lambda. And here, if the order is n, nothing but order. If n is the first maximum, so n is 1. And for nickel crystal, that D, the separation between the planes, D is 0.9 angstrom. So that, and the angle phi is 65 degree. When you substitute and simplify, we get lambda as 1.65 angstrom. This is the value for lambda of the waves here diffracted. See, the diffraction occurs in case of a wave. If electron behaves like a wave, then only diffraction occurs. When electron beam, the wave associated with the electron beam gets diffracted from that. For those waves, the lambda obtained is 1.65 angstrom. This is the experimentally obtained value for lambda. Then, according to de Broglie hypothesis, whenever a material particle gets accelerated in a potential field V, then the lambda of the wave associated with that particle, wavelength of the wave associated with the particle is 12.27 by square root of V angstrom. This one we had seen in the last class. And here, in this experiment, the maximum intensity was observed corresponding to 54 volt. It was observed at the voltage 54 volt, and when we substitute and calculate the value of lambda, it comes out to be 1.66 angstrom unit, thereby proving that the moving electrons, they are associated with the waves, and those waves, they undergo diffraction here. This is, and the wavelength, the theoretical value as well as the experimental value are in well agreement with each other. They agree with each other. This is how Davidson and German experiment proves that. Here the experiment is performed with the electrons, and the experiment, it says that the moving electrons, they are associated with the waves, and this is generalized to any particle moving at a very high speed, nothing but the velocity comparable with light. This is how Davidson and Germer proves the existence of matter waves. With this, I stop here. Let us continue the next class with another topic. Thank you.